my talk is about the storage engine that we built for InfluxDB. Obviously, InfluxDB is an open source time series database. So the storage engine, our storage engine comes in two parts, essentially. The first is the time series database, right? We have a series of values and timestamps indexed so that they're quick to read. And then the other piece is an inverted index. That helps us map metadata about time series to the actual series themselves. So I'll dive into each one of these pieces in this talk. So a little bit of preliminary stuff that'll set the stage. So everything is indexed by time and a series itself, right? So everything is contained on disk in contiguous blocks by the series. We also split things out into shards of time. So in this example, we have a shard per day. And for us, each shard is almost like an underlying database so that it's efficient to drop old data, right? We can just drop those files. So here's what data inside InfluxDB looks like, or what the schema looks like for the time series database. We have a measurement name, which is a string. We have tags, which are key value pairs, and the values are strings as well. And then we have fields, key value pairs, where the values are the actual values that we have in our time series. And then we have a timestamp. And we actually support nanosecond scale timestamps. So actually, one other thing is we support different types of values in time series. So we support float 64, int 64, booleans, and strings. So for our example, say we have a series, which is represented by a measurement name, a tag set, and a field. That's going to be a series. It'll map to a unique ID. So because that maps to a series, what you can think of our underlying storage engine as is it's almost like a columnar store, right? And when you see fields like this, you kind of think of it as like a row, but we don't store it in like a row orientation. We store it like a columnar database would. So then we have, obviously, just tuples of the timestamp and then the value. So when we first started InfluxDB, we used LevelDB as the underlying storage engine, right? LevelDB is open source by Google. It's basically a key value store where the key space is ordered, which makes it efficient for doing range scans through the key space, right? So one way to organize time series data inside a key value store would be like this. You have the key, so you have the ID, and then you have the timestamp, and then you have whatever your value is. So the key is like a composite of the series ID and the timestamp. So here we have a value for series number 2. We see that's next in the range of the key space. So say we insert a new value at a later time for series number 1, it gets inserted into the key space there, right? So having this key space be ordered is essential to being able to do quick range scans across the time series to do calculations, right? Mean, max, percentiles, all that kind of stuff. So yeah, basically just like more data. Now, there are a lot of existing storage engines that have this model, right? LevelDB and all the variants, LMDB, BoltDB, copy and write B+ trees, right? So the real question is like, why in the hell would we actually create a new storage engine? Because that's like the worst possible thing you can do. It takes forever to build it and make it reliable. So why would we do that? Well, first, we used LSM trees. That's what LevelDB is. It's a log structured merge tree. So LSM trees are heavily optimized for write throughput, and you also get compression out of them. So when you think about time series, like time series is a very write-heavy workload, so it seems like it would be a good fit. So one of the problems is that deletes are expensive. So the way an LSM tree works is you write to a log file, and it gets converted into SS tables, which are read-only indexed files. And then a background process will compact them together. So when you do a delete, what it actually does is it writes a tombstone record, And then when you read data, it has to merge the actual index files with the tombstones to figure out what the read should be. And then later on, the compaction process will pick up the tombstone and rewrite whatever file has that tombstone in it. So it basically has to rewrite a bunch of data for the single delete. A problem that we had with LevelDB was because we had organized the data into shards, blocks of time, that we could easily just like drop those databases, we'd have a bunch of open LevelDB databases inside a single process. So we'd end up exploding the number of open files that the process had. So it didn't matter for people with smaller databases, but for people with really large databases that had many shards, they basically would just exhaust the number of file handles they could have open. So the next thing we looked at was copy and write, excuse me, memory mapped copy on write B+ trees. So one thing we saw was that the write throughput on these weren't good, or at least it was pretty good initially, but then as the database got bigger and bigger, the write throughput got worse. And even worse than that, the IOPS would just go insane. Like the IOPS were really, really bad. And for the implementation we were testing with, which is BoltDB, it's a pure Go implementation of this. It's inspired by LMDB. Every time it had to make the memory mapped file larger, basically it would double it as the database grew, it would completely stop the world, right? You couldn't do writes, you couldn't do reads, everything was blocked until you like made this file larger. So if you're going from 256 megabytes to 512, not that big of a deal, but if you're going from gigabytes to many more gigabytes, it becomes problematic because it slows things down. And then the other thing that was kind of a deal breaker for us was there's no compression, right? Time series data, you have a lot of data, so compression actually matters at scale. So none of these things actually met the requirements that we had for Influx and for what we wanted out of our storage engine. We wanted something with high write throughput. We wanted something with really good read performance, right? Time series data is one of those horrible use cases where you have a lot of writes and a lot of reads, and you have reads that are range scans across many, many values, right? So there's that. And then we needed something with better compression. So LevelDB uses Snappy as the underlying compression algorithm to compress blocks of data, which works okay, but it's a generalized compression algorithm. With time series data, it usually has a shape. And you can actually achieve better compression than a generalized algorithm will give you if you bring that to bear on the fact that you're working with time series data. So we also said like writes can't block reads, reads can't block writes, right? We need to always be available. We would rather read stale data from the storage engine than have a read block. And we need to be able to write multiple ranges of the time simultaneously. For us, for our solution, we actually allow the users to set the timestamps so they can write historical data. The data can be lagged behind, which we find is very common in sensor data use cases, right? There'll be sensors, they'll collect data for 4 hours, and then they'll send the data up. So you have lagging collection. We needed hot backups. We needed to be able to have many databases open in a single process. So about a year and a half ago, we started, a little bit longer than that, we started development on what we ended up calling the time structured merge tree, or the TSM tree. So it's kind of like LSM, but different. It's basically inspired by LSM, and it's very similar to that, right? So it has these different components. You have a write-ahead log. You have an in-memory cache. You have index files. That's very similar to LSM trees, right? Wall's the same. Mem tables and SS tables, right, in LevelDB terminology. So going through this, say we have awesome time series data that we're writing in. We write it to the wall, and we also write it to the in-memory index. Once the wall is f-synced, we return a response back to the client. So we know that the data is durable at this point. And then periodically, we will flush the in-memory index into an on-disk index, which is actually what we call TSM files, right? Those are like the SS tables. And the other thing is we memory map those files. So this is a key thing that we wanted to do. It's one of the properties that we really liked about the copy on write B plus trees is they were memory mapped, so it made it so the caching was super easy. Like we got caching for free. The operating system would do it for us. It would make sure to page in what was hot and do everything, and we just let the OS do the hard work. So here's the structure of a TSM file. So TSM files, just like SS tables, are read-only files. Once they're written, there's no updating them. So we have a header, blocks of data, an index, and then a footer. So here's what the header looks like. You have the magic byte sequence that identifies it as a TSM file. You have a version. The blocks of data look like this, right? So we have multiple blocks, and for each block you have a CRC, and then you have the actual data itself, which is just compressed time series data, all this data. And then we have an index. So in the index, we have a key length, right? Because in our case, the keys are actually strings. They're not uint64s or uint32s or whatever. So we need to know the length of the key. Then we have the key itself. We have the field type, right? Because we can store different types. And then the count, and then of values that we have in the file, the min time, the max time, the offset in the file of where to find those values, and then the size. So, and then the footer is basically just the offset of where to find the start of the index. So using all these things, we can essentially use the memory map to jump around in the file without having to, we can just use it like you would an array of bytes. So here's what the compression looks like. So this is what a single compressed block is like. So we have a type at the beginning, we have the length, and then we compress separately the timestamps and the values. By default, we will try to compress as many as 1,000 timestamp value pairs into a single block. So basically, essentially, like when a query hits the database, if we're just querying a single data point, we actually end up decoding 1,000 values to get that. Or if we hit 10,000, then we're going to decompress at least 10 blocks to get through those values. So the reason why we separate the timestamps and the values as opposed to interleaving them, like some other solutions do, is that we want to be able to get the best possible compression for our timestamps. And we do this based on the precision of the timestamp and the deltas. So in the best case scenario, we can use run length encoding. So this is if you have a time series that's sampled at fixed intervals, right? So say you have a time series where you're sampling it once every 10 seconds. So second precision is all you need. It's every 10 seconds, so you can encode it with the beginning timestamp and 10, which is the delta, right? And you just use a var int for that. So essentially, like you can encode 1,000 timestamps in 10 bytes, 10 bytes less, 9 bytes. So if we can't do that, then we jump down to simple 8B. So basically, that's if there's variable lengths. There's this paper, Anna Moffat, index compression using 64-bit words. That's where we ripped it off from, or borrowed it from. And then the worst case is just the raw values themselves, right? The int64 timestamp values. So because we support nanosecond level precision, if you have random events coming in at the nanosecond level precision, but they're spaced really far apart, we're not going to be able to, using delta encoding isn't going to help us at all, right? So float 64s, we use a double delta based encoding. We're inspired to use this by the paper that Facebook released in the summer of 2015. Sorry, yes. It was the Gorilla paper about their time series system that they have. And basically, they had this thing where they used a double delta encoding for float 64s. So that's a good paper. This right here, the link at the bottom is Damian Grisky, who's pretty well known in the Go community. He wrote a Go implementation of this, and we forked it and used it for ourselves because the Gorilla paper actually interleaves the values in the timestamps, and the timestamps are actually 30 in 32s, not 64s. So we had to change it up a bit. Booleans or bits, those are easy to compress. In 64, we use double delta or zigzag encoding. Zigzag's the same as protobufs. And then finally, for strings, we use snappy. We're thinking about adding dictionary compression. I mean, we've been thinking about adding that for like a year and a half. It's just one of the long laundry list of features that we want to get to at some point. So, updates. So essentially, like within our system, a value, like the unique key for a value, like that you would, in a SQL database, you'd have an auto inc, like integer for your row ID, right? For us, it's just a value and a timestamp. The unique key is the measurement name, the tag set, the field name, and the nanosecond precision timestamp. So what that means is if you write one value in, and then later on you write another value into the exact same series, right? Measurement, tag set, field, and the same timestamp, you're updating that value. So what we do is we write it to the write-ahead log, put it in memory, and at query time we resolve that, right? We scan through the index files, and then whoever is the latest one that was written in becomes the value that we use. And then later on, when compactions happen, we throw out the old value and put the new value in. I mean, we're not really designed for updates. It's a time series use case, so our assumption is it's almost always new data that you're piping in. Like you really don't usually do updates in time series. So then deletes, how we handle deletes is very similar to level DB scheme, which is we write a tombstone, at query time we resolve it, later on when the compactions run, we make sure we remove it. So compactions. So basically what we do is so over the course of operation, we're taking in writes to the write-ahead log, and we'll flush them out into a TSM file. So as you're taking writes, like say we flush out like 4 separate TSM files, and over time what we want to do is we want to combine those into larger files so that we don't have a bunch of different indexes that we have to hit to answer a query. So the compactions will take a collection of TSM files and combine them together. And our goal is, for a single series, we want as many of its values as possible to appear in a single file, right? We want to optimize for having contiguous runs of values for a series in each file. So that means the fewest number of series in a file as possible based on whatever our max file size is. So I mentioned before we keep the number of points into 1K blocks. So basically, once we hit 1,000 points, we'll encode that block. And then if we still have more points for the same series, we'll have the next block of 1,000, then the next block of 1,000. So we have multiple levels of compaction, just like level DB. So the compactor has this planner where it says, okay, I'll favor level 0 compactions first, and then gradually over time you'll get larger and larger groups. But the other thing is that for the time series use case, most of the time people are just appending now data, recent data. So what that means is older files, as they get compacted into big ones, we actually don't end up having to touch them. Most of the time we're only touching the recently written TSM files to compact them into larger ones. And then the last thing is we run full compactions. As I mentioned, we still have the database organizing things into shards of time. So basically, if you have a shard per day, after the day rolls over, the database will just wait for a while to see hey, has this shard received any writes recently? And if it hasn't, it will do a full compaction to try to optimize all of the TSM files. And ideally, if you're just writing now data, you won't have to rewrite those again. So we kind of segment this key space by time. All right, so now I'm going to talk about the indexing scheme. So basically, here we have an example query. I'm getting the 90th percentile in 10-minute buckets for the last 12 hours. for every single host. So I'm pulling back a time series per host for all the hosts in the Western region. So the question is, how do we map these things to series IDs, right? Our query engine works in kind of two phases. One is the planning phase, where we say what series are the ones we're working with, and the other is the execution phase, where we actually compute these percentiles in these windows of time. So our solution is an inverted index, right? Now, normally an inverted index, when you think about that, is it's used in document search. It's Elasticsearch, where you're mapping document IDs to terms, right? So the term inverted, you have a list of documents that have the term inverted. And the idea behind the inverted index is you have these different terms. So if you have a query that has like 3 or 4 words in it, you can do unions and intersections on those lists to quickly come up with a list of IDs that match your query. In our case, we want to match this metadata in the query with a list of series that we want to look at. So for this exercise, assume that we have these two series, right? We have measurement, tags, field, and they map to some ID. And then we need to index this data. So this is kind of how we index it, or we think of indexing it, at least in V1 of this, which I'll talk about. V1 is basically what we have right now. It's an in-memory index. So I guess I called the database like 2 engines in one. One is the time series database, and the other is the inverted index. The inverted index on Influx right now is just in memory. So we keep a map of measurement names to what fields they have. We keep a map of tag keys to what values they have. A map, again, of region of that tag key to its values. And then we have posting lists, right? Specific tag key value pairs, and the measurement itself, what series appear in a specific measurement, and then tag key value pairs, what series appear in those, right? So if we have a query, we can quickly do intersections and unions to say what series do we have to work with. So like I said, V1 was in memory. We loaded on boot. So essentially, we'd look at all the TSM files, and we'd look at their indices and say, OK, these are the things we have to load up. What it meant, this has actually recently gotten much, much better in the, I think it's in the 1.2.3 release, which we recently cut like last week. The boot times are much, much better, but there was a problem where before, if we had people that had very large databases, like we have some customers that have terabyte databases on a single server, they would take a while to load up. So the biggest problem we have with this is that it's memory constrained. We have to keep all of this index data in memory, which is obviously a problem. The biggest problem it presented us with is when we're dealing with ephemeral time series. So for people who are doing, say, infrastructure monitoring, and they want to put container ID as one of the tags that they're tracking, so that they can look at per container statistics. Well, containers are ephemeral. You're spinning them up and spinning them down all the time. And what that means is you're constantly adding to this index that we're keeping in memory, even though a lot of those series aren't hot for queries. So it's kind of wasteful. So those problems, like with high cardinality, mean slower boot times and an explosion of memory, which is actually what you see right now in the current version. So index v2, we started this work probably in September of last year. So the goal with this was to make it so the index was combined in memory and on disk. And ideally, we would do the same thing that we did with TSM, which is we would let the operating system handle the caching for us. So as long as your working set would fit in memory, you'd have a good experience. So here's the design behind that, right? Say we have time series metadata coming in, we do a write, and the first thing we do is we say, OK, do we already know about this time series? We check the in-memory index, we check the on-disk index. If it's in neither of those places, we know this is a new time series that we have to store the metadata for. So it's new, so put it in the wall, write-ahead log, just like the other write-ahead log. And put it in the in-memory index. And then periodically, we will flush this write-ahead log to an on-disk index. So this is basically a different index file. Just like with the TSM engine, we have the wall and TSM files. In this case, we call them TSI, like time series index. It's so original. But we write out those files. And then in the background, we will do compactions of those files into larger and larger index files. So here's what a log entry looks like. It's not very exciting. You have measurement, key values, checksum. It's pretty basic. The flag is whether or not it's a deletion of the time series data, right? So we still have this concept of tombstones versus insert. So we only write this log entry when there's an insert. If we already know about the time series, we don't do this, right? Here's the index file layout. It's pretty basic. You have a series block followed by a number of tag blocks, followed by a measurement block, and then the offsets for where we can find the beginnings of those blocks in the file so that we can skip around, right, just like a byte array. So here's what the series block looks like. We have a bunch of series keys, which are those strings, followed by a hash index, followed by series keys. So the reason why we have series keys, then a hash index, then series keys, then a hash index is because by default, we only write out 64,000 or 65,000 maybe, before we write an index. And the reason we do that is because we don't want to have to fit all of the series keys in memory. What we want to be able to do is when we're reading these TSI files and compacting them, we want to be able to stream it to disk, right? So if we have a situation where we have 500 million time series on a single database, we don't want to read all 500 million keys into memory, otherwise it's going to be a pig. So we need to be able to stream that out as we're reading it. And then the index entries. So looking at a couple of these pieces in a bit more detail. So the hash index. The hash index thing I think is actually pretty interesting. I had not actually heard of this technique up until last fall, but it's a fairly old technique. It's called Robin Hood hashing. So the advantages of Robin Hood hashing is you can so basically a hash index, right? Normally, like you have a hash table, it's of a certain size, you have some sort of string or whatever object, you hash it into a location into the table, and you look it up, right? And the trade-off on hash tables is the closer the hash table is in size to the number of elements you're putting into it, the more expensive your lookups are going to be, right? Because you can have hash collisions and all this other stuff, and you may have to keep like linked lists to find like all these other things. So generally, you're going to have like hash tables that are much, much larger than the number of elements you're actually inserting into the table. But with Robin Hood hashing, you can fully load the table or load the table to like 99% and still get really good lookup properties. You don't have to have linked lists for lookups. And more importantly, Robin Hood hashing is really, really good for hash tables that are read-only. And that's exactly what ours are, right? We write them once when we write the TSI files, and then after that, we only read the hash tables. So we don't have to worry about updates, deletes, any of that other crap. So I'll dig into the details of how Robin Hood hashing works. So here we have three arrays, right? Three hash tables. Basically, the top one is just showing you what the positions are in the array. The second one is the actual hash table. And then the third one is probe lengths, which is something we use to construct the table. And then after we've constructed the table, we don't have to keep probe lengths. We can throw it away. OK, so for this example, I'm basically just going to hash like single characters. So it could be a string of whatever length, but to make this easy so it actually displays OK, we're going to hash single characters. So first thing I'm going to insert into the table is A. So I hash A, and the position I get for the table is 0. I look it up. I'm like, wait, there's nothing there. Sweet. We'll put A right there. Next thing, hash B. B, luckily enough, position 1 is what it got. Nothing there. Let's put B right there. So next one, we're going to insert C. In this case, C hashes to 1. And we look it up, and we're like, oh, wait a second. B's there, so we can't go there. So let's go to the next position over. Let's put it over in 2. And then the other thing we do is we say, OK, C now has a probe distance of 1. What that means is that later on, when you want to look up C, you hash it, and it hashes to position 1. You look at the key, and you're like, wait a second, that's not C. Let me move the next position over. And you move the next position over, and you find it. So the probe lengths come into play later. OK, so now we're going to insert D. So D hashes to position 0, which is like, oh my god. We can't put it there because A's there. B is in the next position, but at this point, we've said, well, now we're in position, we're 1 position over. So D now has a probe length of 1. And we look at B, and we notice that B's probe length is 0. So we're like, B, get the hell out of there. D's going here. You can move over. So B then looks at C and says, oh, OK, somebody's already there. Oh, but he has a probe length of 1, and B now has a probe length of 1. So obviously, like, I'm just going to have to go to the next position over. So I go there. B's probe length is now 2, which I mark. And this is how we're basically inserting things into the hash table. So the reason why it's called Robin Hood hashing is the idea is that you steal from the probe rich and give to the probe poor, right? Being probe rich means your probe position is close to 0. So if your probe position is higher than them, you boot them out and you be like, sorry, move out of the way. And what that does is, like, at the end of the constructing the hash table, you can throw away the probe lengths and write that thing. And what it means is you minimize the amount of drift that you have to go through to look up something. Now, there's another refinement on this, which is looking at the average probe. So once you've constructed the table, you can say, what's the average probe length? So in our case, we're just going to say, oh, the average is like 1, right? So what that means is now we store that average somewhere. And then later on, when we do lookups, we hash the string. So in this case, we say we look up D, and it hashed to 0, remember. But we just add the average probe length to it. And that's the first position that we look at. In this case, we found it. In the case where we didn't have a match, what you then do is you fan out both right and left in the different probe distances until you find your match.
So is this all when you have a hash collision? Is that why
Yeah.
you have multiple?
Yes.
Okay.
Yeah.
Which maybe doesn't happen often?
It happens very often if you're trying to fill your hash table to 100%, right? 100% utilization. So if you have 100,000 items and your hash table is 100,000 like slots, buckets, then you're definitely going to have hash collisions. But there's the paper has like some sort of crazy math where they show you that even the worst case scenario, like the number of shifts that you have to go through to find it are minimal. But there's other stuff. Yes.
I think it's really quick. So you mentioned this is old paper. I actually hadn't heard of this kind of hashing before, but cuckoo hashing has got a lot of interest lately.
Yeah.
Which seemed to actually give the most you can have like 2 hash positions, and you could possibly bump people. But it seems actually a simpler construction. I was wondering if you considered it and why you went with this approach. Or?
We had, or at least by we, I mean people on my team.
And for some reason,
and they had decided that I actually have not read the cuckoo paper yet. I read the Robin Hood paper. I don't think I've read the cuckoo paper, so I don't remember the details. But basically, they said like, this is easy, and our use case is like kind of a weird mutant use case in terms of hashing, right? Because we like write the hash table once, and then we only ever read from it. That's it. So yeah, it makes it kind of special in that way. Cool. All right. So that's brief introduction to Robin Hood hashing. there are a couple of if you look up Robinhood hashing, there are a couple of good blog posts on it. Like the first and the third results you get on Google are actually quite good that kind of explain it, and one of them has like example C++ code that you can like dive through. Okay, so then the other thing we have is we keep sketches for cardinality estimation, right? How many measurements do we have? How many series do we have? How many tag values do we have for a given key? For that, we use hyperloglog++, which is like a refinement on hyperloglog. I'm not going to go into the details of that one. You can look it up. Yeah. But that is all I have. So any other questions I can field or anything? Yep.
Why would average distance be preferable to like the distance? The lookups are somewhat evenly distributed.
Oh yeah, the median's probably what you want actually.
Yeah.
Yeah.
I figure you're just showing the example how it works, but even
Yeah.
the average is similar.
Yeah, so there are a couple of that's only one of the possible refinements you can do. I think maybe the paper does or other people list like 3 I think possible like different ways you can do lookups on the hash table, and they have different. I think some of them are good for some cases and better for others, or that kind of thing. Yeah.
Who determines the size of the hash table? Do you ask the customer to try?
No, the hash table is defined by, like I said, we were for the series blocks. We only encode 64,000 series in one block, so 65,000. So that means the hash table is 65,000 elements. Basically, like we know how many items we're going to encode, and we set the size of the hash table to that exact number. Or we have a loading factor in there, but I think we're either like at 100% or very close, like not within 95+%. Yeah.
How do you deal with updates? I know you said, Master Security doesn't have update functionality, but I'm thinking about use cases like, streaming jobs and batch job merging, or like, use cases of Lambda architecture, where you might need to update data at a data point in time. So are there any use cases that are running on InfluxDB that need to update?
So the question was, how do you deal with, I forgot, I'm supposed to repeat the questions because it's getting recorded. How do you deal with updates? So we can do updates, but even in the example you gave, which is you have Lambda architecture and you want to like do things, like you don't need to update. Those are all individual events that occur, and there are other ways to tie that data together. Like you still want.
Instead of putting any application logic, do you natively support anything like that?
And we support updates, absolutely. But again, like that's not the optimal use case. The optimal use case is you're writing new data. So, yeah.
So for your V2 of the reverse index there,
Yep.
Have you measured what the balance is between CPU utilization of updating that index on every write versus updating your time series data?
So the question was, have we measured like the I/O versus CPU utilization on the new index when we're updating?
Yeah, and the balance between the two, because when
Yeah.
you scale up, maintaining that index on the same machine.
Yeah, so the new index is actually available in the nightly builds for 1.3 right now. You have to turn it on to enable it. I have a blog post I wrote a few weeks ago that shows you how to do it. It's like a config option. The I/O load is really, really low because in most cases, like you're not inserting a ton of new time series data. Like even in a container use case, like how many unique, and you're flapping containers all the time. Like maybe you're writing a few million new time series per day, maybe more, but it's generally we're not writing to disk for that. I mean, we tested writing. So far, we've tested up to 500 million unique time series on a single box. But the thing is, when you think about 500 million unique time series, you have to write 500 million individual data points first, And then to get a stream of values, like if you want to write multiple values per series, that means 5 billion data points is still only 10 values in each time series, right? So it takes a long time to, like, what dominates is not the creation of the new time series metadata stuff, but of all the other overhead with taking that in. Yeah. All right. I think that's it. Thanks, everyone.